Ok, bueno, muchas gracias por su asistencia y bienvenido al Seminario de Ingeniería Matemática y Computacional. El día de hoy va a presentar Clement Lezane, que está visitando el IMC hasta la próxima semana, así que, de hecho, si quieren conversar con él también, pueden contactarme a mí y yo puedo hacer el contacto con Clement. Clement es estudiante PhD en la Universidad de Twente. Está trabajando conmigo y también está investigando con Alexandra Bromont de École Normale Supérieure de París. Y bueno, el trabajo de hoy se enmarca dentro del contexto de métodos que involucran, bueno, yo me lo voy a explicar, pero una descomposición del objetivo que tiene un término estocástico y un término de regularización.
Thanks for the introduction. Hi, I'm Clement, so thanks for coming there. I'm going to talk about my work, but as I would more likely talk like the important notion in my work, not the entire work, which kind of long, and then I want to not like kill you with all the details. So if you have interest, we can talk about later. Just gonna do like a general introduction and then some key elements in my work, for my work. So here, so we're gonna follow this kind of scheme. I'm going to do some introduction, and then going to talk about a lot about conjugate number because it's really important problem. And then we're going to talk about the extension, which is actually the paper and we are working with Alex and Christopher. So the mirror distance. So to understand the mirror distance, we first need to talk about a little bit about the Bregman divergence. So I'm not sure that if we are all really familiar with the Bregman divergence. So let me introduce. So the thing is that imagine you have like a convex function, a potential function like omega, right? And then the idea of the Bregman divergence is you have 2 points, x here and y here, and then the Bregman divergence. So the Bregman divergence say that it's the value between 2 points x and y, such as it's like going to be like, so you first mirror like the height difference here, right? So this time, so here you have omega x, and here you have omega y. So Bregman divergence, the first is like the difference between the two potential, and then on top of it, you're going to retreat what is the derivative for the second point here. So this part, you're going to slack it away, and the remaining part is going to call the Bregman divergence of the x for the pair x, y, and for the distance generating for the potential function omega. So we know that, so first thing we notice is that this is always positive for like convex function. And the second, so it's going to be always something positive, that's good. And the second thing we notice is that it's not necessarily always equal to yx. Why? Because, well, here we are like in the Euclidean case, so if everything works well, but technically, like taking the derivative of the second point y is not the same as taking the derivative of the second point x. So you cannot just alternate them obviously. So here we are really in like in this graph we are really like in a standard case when you have like, for instance, we are like in omega, which is like the Euclidean norm, and in that case, for example, the delta omega of xy is going to be like x minus y squared. So in that case, then this is the distance, but that's not the case. But that's not all the case. That's not always the case, and that's why we call it a divergence, another distance. It's not symmetric, and it's not always symmetric. So this is like kind of important for like convex optimization, so the Bregman divergence. And then if once you are familiar with that, then we can think about to introduce our problem. So the idea is that we're gonna try to minimize function f or on the setting big X, and then like what people used to do with that. So first we need an assumption for that, and then assumption is going to the people used to take is to say that okay, what we know about f, we kind of need kind of a lower bound and upper bound. So we need first an upper bound for the Riemann divergence of F. We suppose the Riemann divergence is going to be smaller than norm squared, LL. This is like what we call like kind of the smoothness. This is like an upper bound for the Riemann divergence. And then also in the literature, people also consider a lower bound, which we usually call the mu strongly convex, the strong convexity, which is that the same stuttering, but this time it's a lower bound corresponding to mu. So one thing that we can all notice is that if this is true, then L is bigger than mu, because the upper bound will be bigger than the lower bound, right? So this is something that's usually considered. And then, okay, so this is the assumption, and then how do we solve it? So now we're going to suppose that we suppose that we are in a stochastic case. It's a little tricky. So we don't have the exact gradient of f, the function you want to minimize, because if you had then you can just do maybe the gradient descent also. But here we are like in the stochastic case, so we have an unbiased estimator, which means that we have like G the estimator, and nabla is the exact gradient. So we suppose it's unbiased, so it's 0. But somehow we also need to suppose something about the variance, which is that we have to suppose that the variance has a dual norm which is finite. So what's the dual norm? The dual norm is defined as this way. It's like when you have a norm, then you consider the staggered product, and you can always extrapolate a dual norm. And we have to suppose that that dual norm has a finite variance. So these are like this is linked. If you want to do something stochastic, these are the usual assumption we need to prove the convergence. So, and then the algorithm says a little bit different is that instead of saying that I'm going to take xt, I'm going to just subtract by the gradient, which usually call gradient descent. We're going to do this following. We'll try to minimize the function with the estimator and the d, which is the proximal function, which can also be called omega here. So I mean the d omega, the Riemann divergence of the omega. So, and well, maybe that's not super common, but sometimes people instead of minimizing this function, they say that we have to we have to solve GT. I mean, if you pick up this case, for example, then you see that what we are doing is that we are always computing the minimum over alpha t plus gamma t x minus xt squared, right? So you can see that with the general solution idea is that you're going to try to find the minimum of the solution, but not too far away from the previous point. So this is why also this kind of the mirror descent is also part of method what we call the proximal gradient, is that you don't want to go too far away from the previous point. So those are like interesting property, but then we see how does it apply in practice. So why we call this mirror descent is because whenever we try to compute the minimum of the function in this form, we can see that in some way is that this is the original problem on the polyhedra, and then instead of doing the gradient descent here, because we want to do it on another space, using the proximal function. So why is that interesting? Is because sometimes you cannot do the descent here. One example is that, for example, if you're computing a function with the variance, then you don't want to do a gradient descent on the variance. Why? Because what happens if your variance becomes negative? If you do a step size, at the end of the outcome of your xt is negative, and it was supposed to be a variance, then you lose all the meanings, right? So what people used to do is that instead of computing the gradient descent on the algorithm, they will consider, for example, the logarithm function, right? And if you do logarithm minus the other logarithm between the variance, then you still stay positive. And this is actually the idea of doing the gradient descent in the dual space, and then you come back later to the original space. This is one way to see that. And then so the formulation is that you're doing it on the nabla d instead of the original space. So this is why we call it mirror descent. Okay, so now we can finally show that the first result. So this is so George Land has worked a lot on that. And we have updated part of his work to this result. And this is actually a classical result, which is that okay, so if you choose alpha t and gamma t in some way, then here you see that this is the gap between your current solution and the optimal solution. X star is the optimal point, plus the distance is always positive. And we see that this point is going to by smaller than 3 terms. We will see progressively what does this 3 terms mean. So first thing first, we notice is that here we see appear a very interesting term, which is the L divided by mu, which is the constant which is the smoothness constant divided by the strongly convex constant. And this is what we call the function number. What we're going to notice kappa in the presentation. And we already say that the kappa is going to be bigger than 1. And later we're going to see that kappa can be sometimes really big and can increase the dimensions, and that can cause us a lot of problems. So here for now we just see kappa is like something we need for to choose the set size. And so now we come to the third. So AT is the sum of alpha t. So what I'm saying in this result is that the optimal gap plus the distance is minimized by here, this first term. So this, you can say kind of the distance between the optimal point and the starting point. So this is like what we call initialization error. Here you have like the alpha t, which is the number t scalar something. So we remember this is the difference between the exact gradient and the estimated upper gradients. So in expectation, this term is 0, but in variance, it can be pretty big. So this is like the bias. But because we are in unbiased, so when you're going to look at the expectation, this term will not exist. And here you have C something square. But actually, this is, if you look at carefully, you have to see the dual norm square, and this is nothing else our variance. So basically, what we are saying is that the optimal gap is upper bounded by the initialization error, the bias, and the variance. This is one way to see the dispersed result. Okay. So now we say that we see some condition to choose alpha t and gamma t. Then how can we do it in practice? Well, you have a lot of possibilities, and one of them is just to consider alpha t to be something that's linear, depending on the kappa, and then gamma t, which is quadratic, is that. And if you consider this approach, to that side, then you have immediately like you use the 1 and you take the expectation. Then of course the bias error goes away. So the initial error becomes in this way, which is kappa squared times the initial distance divided by t squared. And here you have the sigma squared divided by mu t, which is the variance term. So here with k1 and k2 some arbitrary constant. This is this constant. So in our work in most work we don't really pay too much attention to this term because they don't really depend. It will not really increase the dimension or the dimension of the problem. So this is something divided by t squared and mu t, which is pretty cool. But we can do better, and especially when kappa is going to be big, you can see that this term is not optimal because you have like t to be bigger than kappa. If you want this term to be like smaller than 1, let's say so, right? You need like to t squared to be at least bigger than kappa. So you need to do something, and we'll see. So we will see first how big will be the kappa, and then second how to improve this algorithm to make it better. So is there any questions so far? The first part right now, so
Go back to the algorithm.
Yes.
So this is the non-accelerated.
This is a non-accelerated version.
So why in the upper bound there's a 1 over t squared?
Because
you're tuning
because the accelerated method will
you get the kappa.
help you to not have a smaller kappa here. Yeah, it's like a spoiler, but you're gonna have like kappa instead of kappa squared or like the accelerated method, and that actually can be a lot of improvement. We will see later why kappa can be that big. So people usually think that the t squared here is optimal, But in our setting, it can actually be bigger. It's not it's not lower bounded by t-square. You can go even for faster convergence. Any questions? Okay, so we're gonna see like when this kappa can be pretty big. So for instance, there's like originally appearing like necessary work, and later in like one of the paper with Christopher and Alec and Jackie, they have like shown that actually whenever you look at the regression problem on the LQ norm, then for function if it's at the same time L smooth and use strong equal-x, then the conditional number will inevitably increase with the dimension. So here it's a mistake, it's the Q here. And yeah, so 1 minus 2 divided by Q is going to be bigger than 0. So you can see you're going to have a conditional number that increase with the dimension. And consider like if you like have D which is equal to million as for neural network, then you have a really big condition number. So yeah, as a reminder, so the LQ norm is for each coordinate, you take the absolute value, you elevate it as the Q exponent, you take the sum, and then you divide it by the 1 over Q. You take the 1 over Q exponent of the sum. For instance, like Q equal to 2, you have the Euclidean norm, right? You have just like the square root of the sum of the square. But what is a little bit funny is that here you have for the LQ norm, which is just simply like a generalization, you have this problem of the condition number. So the proof might be a little bit long, but I think drawing is the proof maybe like more interesting, and then to read the exact proof. The proof comes from the fact that there's a really interesting geometry of the LQ space, which seems a little bit not usual when you compare with the Euclidean space. So first thing is like, okay, so I'm gonna try to plot the thing is that, okay, so if I want to build orthogonal families, each time I just take like a unit length, and my question is that how many I want to build like D intervals like this, all equal size. They're all, well, here is, I cannot draw n dimension problem on the 2D table, unfortunately. But the idea is that what's the unit? So I want to change D interval of U size U, like unit, and I want the big, so I start from 1 and I want to end at the unit ball. And like what's the unit of U when you consider what's the like how many like unit interval can fit in like a unit ball? That's like a kind of funny question, right? So the answer, well, maybe like in the Euclidean is obvious, but in the LQ space, the answer is 1 over. So I have is 1 over D. Thank you.
Actually, maybe the L infinity case is easier to explain, right?
The L infinity case. Oh, for L
infinity.
Yeah, you can. Is it?
Because you can move as far as, like, you can move in orthogonal directions, but move as far as 1 in everyone, and you stay in the cube, right?
Yes. But then yeah, I need to do the proof.
You need the general formula, but yeah.
Okay. Well, the idea is actually you can consider like so here what we are doing is that we're going to try to build this. So we're going to start from a point x0, and each iteration we're going to choose like delta e. So delta is like so. I'm going to so 1 over d, 1 over q. This is like the step size, and yeah. So the idea is that if you do this 1 over if you look at the LQ norm of something which is when you look at the LQ norm of something which is written in this way, this is going to be equal to 1 because this is equal to the fact that you're like summing over d equal to 1 to d of something that's always in power of q, right? 1 over d, and that's equal to 1. So this is where the 1 over q comes from. And the idea is that, okay, so you have this way, but then what does the strong convexity means? The strong convexity, so our argument is that if you choose the sign of delta k correctly, we're going to try to create from the 0 some point which always point in the right direction, such that when you look at the because the strong convexity basically also gives you some argument about the points. So what I'm saying is that you know that for example, the Riemann divergence of the k point and k plus 1. So you have xk here and you have xk plus 1 here. I'm saying that Riemann. I'm saying that the Riemann divergence between sk plus 1 and sk point is going to have to respect the strong convexity, which is going to be mu divided by 2, and then the sk plus 1 minus xk squared, right? This is the strong convexity. If I count the distance bigger than the norm square, so here we are in the, and then what's like the distance between LQ norm between these 2 points, and this is just equal to d 1 over d 2q, right? And yeah, I'm gonna take, and then this idea is that when you do it all together, the thing is that from the original point, so this is an approximation of the solution. The idea is that when you have like so we are computing the distance from here to here, and each coefficient is going to be bigger than 1 over d to q. And the question is that how many you have them? You have d over them, right? So you're going to have mu d 2, and then here it's going to be multiplied by d 2 over q, which is equal to mu. So this is from the strong convexity. So we're kind of saying that when you look at kind of the distance from this point to this point, it has to be bigger than mu d over q. And however, it's kind of like the Riemann divergence. It's a Riemann divergence of xt plus 1 and x0 from your final point to the original point. Sorry? Yeah, it's kind of like, but the thing is that Riemann divergence is not the distance. So you cannot say use the, and also the Riemann divergence I mean, the inequality works in the other way around, right? You say the sum is bigger, is more than the normalness, yeah, and not in this way, but it's more like a telescopic way or a reason for using the internet. Yeah, and then also the orthogonality saves us. We suppose that we are in orthogonal families. So actually it can be seen as triangular inequality, but then just each of the component is like orthogonal, so they can just be summed together. Right. So, and then however, so we have this term from the kind of the distant term, and then we also remind that the function has to be smooth, has to be L smooth, which means that this term is gonna also be like smaller than L2 plus something LD plus 1 and x0, right? But this is just equal to 1. So what we have is that L divided by 2 is bigger than mu divided by 2 times d over 2's cube, which means that L divided by mu, the function number kappa, is going to be bigger than something. So that means that the is such a function. So this is a little bit unfortunate. If you use that just like the traditional way to do the optimization, then you have this problem of condition number going increase with dimension. But okay, so kappa can be pretty big. Then how do we solve that? So the first idea that we can solve that is to use like a restarting algorithm. So the main motivation for the restarting algorithm is that when you look at the previous bound before, right? You have like something, the gap you're interested in, plus something positive, which is smaller than this. So naturally, people, you say, okay, this is positive, so we can just ignore. But here, the thing is that this term you might be ignoring will appear here, which means that the initialization error, you have actually a relationship between the final bound and the initialization error. So if you can like set this term to be like arbitrarily small, then you can have say this term will be arbitrarily small, and this is important because this term has a kappa squared inside, so this can be pretty big. So the idea is that if you can find, so for t, for example, equal to kappa times k1, you're going to say that this term is going to be smaller than 1/2. So what I'm saying is that using a constant number of iteration will allow you to decrease the initialization error by 2. And this is what actually makes appear a recursive form of that. So the idea is that you're going to try, the idea is that, as I said before, you're going to try to restarting the algorithm with a constant iteration k, and do it n times. And then for each time, you look at which point you're stopping, and then you start from, and for the new iteration, you start from your previous stop points. This is why we call it the restart, because you just forget all what happened before, and you just take the new endpoint, the endpoint as a new start point, and you do it n times. And then once you finish it, you just run your algorithm normally. Okay, so what does it bring us? Well, it brings us that when you consider your algorithm, so when you look at the researching lemma tells us that if you do this, so if you have like an algorithm with this recursive form, and you do the previous restarting program algorithm, then you're gonna like divide it by the initialization by 2 in power of n, so divide like really exponentially fast with the cost. The cost is that instead of paying k2 t alpha a, you're gonna have to pay the double. So you are like this recursive form allow you to reduce considerably the initialization error term, like exponentially fast, but that will have to in the price of doubling your variance. So okay, so that's also cool. Then what if you well, we can directly apply if you apply, yeah. So if we apply this algorithm here, I think I didn't draw the slide, but generally you're going to say that using the restarting algorithm, you're going to say that f of xt plus 1 minus h aggregated points. Yeah, we take the middle point of the point because it's like IgG. You don't really ask for you don't take the performance of the only one point, but you take the average with all other points before. That's to use the convexity f of x star. So if you use the other lemma, then you're gonna have like something like k1, or let's forget about the constant, and then you're gonna have so we're gonna forget about the absolute constant for now, and then we're gonna have kappa. Sorry. X. we have n plus 1, and then plus the, so 2k2 minus 3 divided by t. So we are like doubling. So we kind of have like form, but we can do it better on the kappa squared here. And so now we're gonna talk about other thing which is more common, which is about the accelerated method. So this is the other trick we have for like when you have big condition number. I'm not sure if everyone's really familiar with the accelerated method. The idea is that for the smooth problem, because we are optimizing a convex function, so instead of choosing so instead of taking the gradient at the point as when you at iteration t, instead of taking the gradient as a point xt, it might be better if you consider all the points before and you take a convex point, a convex combination point, and you take the gradient here. So take like, for instance, like imagine like you are doing the iteration here. The idea is that instead of doing when you look at t, instead of computing the gradient in the xt, you want to make like a middle point from xt with all the points before, and the convexity will assure you that the gradient at this point will guarantee you a faster convergence of the point, and that's actually what you see here. So xt MD stands for middle points. It's like a convex combination between the aggregated points, so the inertia of all previous points, and xt the current points. I mean
That's the somebody on Zoom.
Okay.
It's okay. But by the way, I do have a question. So H should not be there, right?
Oh yeah, H should not be there. Yes, like yeah.
Because I mean, it otherwise looks exactly as the same algorithm as before,
Yeah.
but you're just picking different points where you evaluate the gradient.
Yes, H is 0 here. We are not.
Está bien ahí. Ya lo apago el micrófono. Pensé que yo salgo. ¿En serio?
Mistake. It's kappa here, not kappa squared. It's because it's due to the framework. Okay. Was there any question? So the accelerated method is that you just take like the middle of the accelerated method. The idea of accelerated method is you just take the gradient not at the exact point, but from the convex combination of all the points before. And if you choose the weights correctly, then the algorithm will converge faster. This is the main idea of the accelerated method. So we can then skip all the proof about how to make it. But then, and then you can choose similar step size, which is alpha t linear and gamma t quadratic. And then this time, instead of having kappa square here in the original term, you're gonna have like kappa. You're gonna have like kappa. So this is smaller because kappa is bigger than 1. And here later, when you look at using the realizada algorithm, then you're gonna have like something square root of kappa instead of kappa. So in the non-accelerated method, we have kappa in terms of the complexity, and here we have square root of kappa, which is better. And then the other term does not change. But actually, one thing we noticed that this term is not changed. Sigma squared divided by mu epsilon, like accelerated method here in our case does not have any effect on the stochastic noise. But that's actually not. But that's not that much surprising because this term is already optimal. Like you can, I mean, up to this term is already optimal up to a constant. There is no way to make it better in the settings. So okay, so then we can talk about it. So all I've done before, it was like a little bit of mixing of the existing literature and what we have updated the proof. But here we're gonna talk about something that's really new in our paper and not much treated in the previous work. Any question on the? There was a question about like mirror descent or function number.
Just trying to listen. So kappa is exponentially gain, right?
Kappa is exponential. No, kappa is a polynomial. Can be a polynomial indeed.
Right.
But it's really problematic.
But then you divide it by 2 to the n. So n is it's about.
It's a cube. So cube is a dimension.
No. He's referring to the accelerated rate. Maybe you can go to the previous slide. I mean, it's true, but even to kill it off, you see that. I mean, okay.
I mean,
maybe you can write the upper bound with the restarts, not the complexity rate, but not the complexity bound, but the upper bound in that form.
Oh, okay.
Right, because the question is basically when are you going to kill off this kappa term in the convergence rate, right? Is that?
Yeah, I mean, I don't understand why the complexity is square root of k and not like log k first. It's divided by 2 to the n, and then you have to kill kappa. Yeah, maybe I'm a bit lost.
Okay. So one way to not get lost, I think. Yeah, I didn't precise. I think it's my bad. Okay.
The tricky thing is like this n is not the number of iterations, right? It's
Yeah,
kind
it's
of
not
the number of rounds you
Yeah.
perform, and every round has length
Of k.
k, which is unspecified. But when you kind of unravel that, you will see that basically there's
So it's not constant.
it's not going to be an absolute constant. What's the length of each round? I forgot. in this case.
It's here. It's something which is
You need to have this thing. Yes.
you want this term to be smaller than 1/2.
Right. And then you have this kappa factor. So then you see that the length of each round is going to be. Like if you have this alpha 1 is 2, you see that you need square root of kappa iterations to have this thing.
So yeah, basically you want this. So kappa is going to be kappa is going to be sorry, k is going to be 2k and 2k1. Right, and in our case, alpha 1 is equal to 2. Right, so in the non-accelerated, you can choose k, which is equal to non-accelerated. You have like non-accelerated, you have k1, which is equal to kappa square, right? As I seen before. So here you have gonna have like 2 kappa square divided by 2. So this is just square root of 2 kappa, something which is where is kappa, right? So each n iteration, one of the n iteration will cause you kappa term the complexity, but for the accelerated version, you have k1 equal to that kappa, and here you have, that's why you have k, which is equal to 2 kappa square, and then yeah, this has something like square root of kappa, and that's why yeah, I think I skipped some notation, but here that's why you have like square root of kappa here. So each iteration, each of the n iteration, you pay a square root of kappa in the accelerated case, and you have to pay kappa in the non-accelerated case. So that was the step here. We want to
Summarize.
okay. So and then we're gonna talk maybe about the work we have done with Christopher and Alex in the paper. It's gonna say the thing is that okay, so what they have done is cool, but what's generally can happen also for the maybe your function is not entirely smooth, right? Maybe you can have a non-smooth component. And then that's why we have like this is also the work being done by Jordan. They introduced like the H, a regularizer function, which can be a non-smooth, but still convex. And here, so and yeah, so for example, an example I can think about is, for example, rich regression. So basically solving the regression problem here, but you plus a regularized term. That's like pretty common format. You can see it. And the idea that how do you solve these kind of problems? So George has in the George Lamb paper, they suggest F to be strongly convex and L smooth as we have done before. Here in our case, we want to do something. We have support something new, which is that we try to support the complementary settings, which is as which is F is still gonna be smooth, or weakly smooth. It's like an extended version of the smoothness. I'm going to support this time H, the regularizer, to have the strong to have this term. And here, you have the advantage here is that here, the mu which is linked to H. When you look at the new condition number, if you have to look at the new condition number L divided by mu A, then we don't have this bond anymore. That because what we are saying is that L divided by mu F, the strong convexity of the loss function here has to be bigger than that, but that's not the case if you look at the if you just pick another function, right? I mean, this was true because you were looking at the condition number of the same function. Here you have two functions F and H. So the strong the convexity of mu linked to H can be anything. Can be anything you want to parametrize. So this was the initial motivation, and on top of it, you have added the exponents, which is Q and kappa. So Q is going to be supposed to be something bigger than 2, and kappa is to be something smaller than 2. So Q is going to be bigger than kappa all the times, and they can be equal if we are in the previous case. And then we are going to support something similar, which is that we're going to have like an unbiased estimator. We still need something. We still need it to be unbiased, but this time we can have a little bit weaker assumption is that we can suppose it to have like a piece moment finite. And then we need something else, and even more fancy on the step side. I can see bottom. But the idea is that if everything is respected,
you go back. So these assumptions when Q is equal to 2 are the
same than before, because yeah, so 1 over P, Q and P are the Holder conjugate. It's like when Q is equal to 2, P is equal to 2 as well. But when Q will, for example, go to infinite, then P will go to 1, for instance. And then because we are only considering the case when Q is bigger or equal to 2, then P is going to be always smaller or equal to 2. That's why it's a weaker assumption. And then we have like some theoretical result about the conversion rate. So here the idea is very similar. So for the expectation rate, you're going to have like the initial error here. Here is like the variance term, but here you're going to have like a new term here, and this is what we. So I have not introduced R, but R is like something linked to the Q and kappa, and the idea is that when Q is strictly bigger than kappa, then you have to pay an extra geometrical cost for your function to solve the problem. And in one of the paper of Christopher, they have shown that this kind of term is like unavoidable, and even worse, this term is like really tight. You cannot make better than the polynomial convergence rate for this new cost. Okay, so this has not worked, and then just a little bit more detail about for the stochastic case. So I say it's a weaker convert. I say it's because when you look at this term, P divided by Q, this term is always going to be smaller than 1, right? So because P is the converse conjugate, Q is bigger than, because P is always smaller than 2, and Q is always bigger than 2. So P divided by Q is going to be always smaller than 1. So we have a weaker convergence. And the question is that optimal? Because we were like really used to this sigma divided by mu t, sigma squared divided by mu t in the literature. And the idea is that it is optimal due to the fact that we are considering a much weaker assumption of on the moment on the estimator of the gradients. Because so let's just this is not the proof in our paper, but this is just an example to show why the moments of a function can be really important for the convergence rate. It's like imagine you have like RAD, t random variables, right? And they have like p moment finite with p something between 1 and 2, right? So and then you want to say, okay, then I want to compute the mean of this function. I want to see that how fast they should also be converted to 0, but I want to see that how fast they convert to 0. And the idea is that if you write in this way and you get Jensen, if it's Jensen here, you have like convergence to the LP norm, and then you use the convective to get it up. Then here you're going to see appear a really current term, which is t divided by t in power of minus 1 over q. So when q is equal to 2, when p is equal to 2, q is equal to 2, it means that if your function has a finite variance, then the mean is going to converge as the sigma divided by square root of t, which is pretty common. But if ever p goes to 1, as the convex conjugate, q will go to infinite, and then t, and then 1, we're going to have like an exponent really close to 0, and that means that the convergence rate of the mean is going to be really slow, and that's what
So this can only be true in expectation, though, right?
It is in expectation.
No, but even the inequality in the first line, I think, or not.
I don't think I only introduced it here.
You say Jensen? That's okay, yeah, you're good.
So this is one example to show that if you have really weak moments assumption on your stochastic approximation, then you have to expect that your stochastic convergence rate to be really slow. Your current to be really slow, and then you can do some fancy regression. You can really like extend the rich regression with like to the LQ norm, with like also the LQ with something which is uniformly convex, like the regularizer, and then you can have like similar result. And the main idea is that in that case, the condition number presented in our paper is going to be much more robust than the one presented in the current literature, and that makes that to achieve like such a precision, the epsilon equal to 0.001, then we need much less iteration than the other paper would need when the dimension increase. And so it was a little bit long. So really take home message is like a condition number is something really important for like a smooth optimization. We will see it anywhere, and then the complexity of the complexity to solve a problem really depends on these numbers. And this number can be pretty big in the non-Euclidean space, as we just seen for like the LQ norm. And so the idea of different algorithm is always try to minimize it. So that's why we have seen like restarting algorithm. We have seen like the accelerated method. Both are like this. And then in the end, also one of the things we have seen in the work, like the moments order is something really important to the convergence rate. So those are like the main message, mainly about how to deal with condition number and how to deal with moments order. And thanks for your attention.
So there is time for questions. So in your numerical experiments, those were for which dispersion?
Yeah.
And what was the distribution for A and B?
Yeah, so A and B and A which is uniform, I quickly pass. So A is uniform and then B is linear.
Okay. Yeah, this example actually, we found it in a paper from the 90s where they said that basically when you have Gaussian noise, right, and maybe you have a prior distribution on the predictors, which is supported on different LP balls, actually, just the maximum likelihood estimator is written exactly this way. It's not a completely artificial problem. Any other questions?
Just wanted to understand, so, you must making you present function that you want to minimize as a sum, right?
Yes.
One is A.
Yeah, which one is smooth, the other one is.
And the other, so if, but I just want to understand, so let's say I have a constant function, then it's L smooth, like is it constant zero? Is it L smooth or not?
It is smooth because the Bringman divergence is 0.
Well, the thing is, you didn't explain the algorithm here.
Oh,
right?
yeah.
So
I just thought that if I can take f of x is 0, then I have only requirements that h is, it's a like, said it has to be m mu convex. That's the function that you.
yeah. I mean, you're saying if I want to deal with the case of just a uniformly convex objective, I can ignore f, assume it's 0,
Yeah.
and then I get something, right? The thing is, like, this algorithm is gonna heavily use the structure of H for its steps. So you really assume that the regularizer is something that you kind of can deal with. So in particular, you solve problems that involve H itself, not an approximation to it. So maybe you can go to the slide where you had this typo, because that's exactly the algorithm that we use. That one.
This one.
You kind of linearize the part that you can, which is F, but then H, you just keep it as.
It's actually this algorithm we use in our work, but we just choose alpha t and gamma t in adaptive way.
I mean, you assume that you know h like exactly, not
You suppose that you can compute h, but not necessarily the gradient of h.
not the gradient.
Yeah,
I mean, you must know a lot of H for doing, even because how would you implement this? You would write the first order optimality conditions for this problem and try to solve it somehow. That would require, I mean, that way of computing it requires computing the gradient of H.
yeah, it's always you need some assumption to be easily computed.
Yeah.
But we have, I mean, it's done in the it's written in the paper, but we have not that much discussed here.
But the rationale behind this is the fact that H is something that is under your control. You propose a regularizer for a certain problem, so you kind of understand it well enough. As opposed to F, which F maybe is like a data-driven loss function, which is pretty
Okay,
arbitrary.
so like model is that if you have some functions you want to minimize, and you can subtract some h with some good properties that you well know, and then you can achieve something better than the module.
If you regularize your problem, it's going to be easy and easier to solve. But then you have to always find a good point, because if you put it way too heavy for the regularizer, then the solution you're going to find is not close, going to be close to your original problem.
Just a very short question. So in the, then we're not doing experiments again. So in that objective function, you can actually compute the expectation. And so my question is, have you compared the performance of your algorithm to the performance that you would get if you actually minimize the closed form expression for that function? Like the comparison of how large is the price that you're paying for the stochastic part. You know what I'm trying to say?
Oh, yeah.
You got the X star, right?
Yeah.
That's
Yeah, because Right, so since you know the distributions and they're kind of easy and it's a quadratic function, you can compute that expectation and then you, I mean, how much faster would it be to actually use the explicit form for f of x compared to the stochastic algorithm that you were I mean, maybe it's an interesting experiment.
But I guess in that case, I mean, because like if you have a bunch of data points, you can write your loss function, right? But if you look at 11, that is not really what we want to do, right? But what you're saying is like if I have
right, so
I have access to the expectations here.
right. Because I mean, we know that right, if you cannot compute the expectation, you're going to pay a price for discussing the second part, that you have to use samples. And then you have your algorithm that seems to perform very well. My question is, in this case, how close is that performance to what you would have if you optimize this as a deterministic problem? Like, are you still very far? Are you kind of close?
In this example, you have the DF, which is explicit. Okay, so that's enough for proceeding. I would say in that case, it kind of reduces to the deterministic setting, which basically there were three terms that you were showing, right? There is an initialization term, a geometric cost, and the variance term. Right. Basically, the variance term dies there, but the other two are still gonna appear.
And also in this, it depends of course on the parameters. I think in for this table we have chosen like the variance term small. It's we didn't choose like a big variance term. That's why I think if you look at the convergence rate, you don't see like if you look at the biggest sigma, you will see like much more oscillation.
Yeah, I mean this kind of upper bound shows that basically the objective has like a region where it behaves as a deterministic optimization problem.
Okay.
And then at some point, basically the randomness kicks in and you see the usual things you would see in a stochastic approximation. So and yeah, these results are, for instance, showing that basically you cannot even see what happens in the stochastic region because of the scale of the plots.
And the transition between those two stages is because of the weight of the regularizer or something more?
It has to do with that, right? We made experiments with. Yeah. Other questions? Okay, let's thank Clement again.